Faithfully convey value. Interpret great books from around the world. Hello, this is Sally's Book Club. Today, the book we're exploring is called Chasing Vulcan. Its subtitle is How Einstein Destroyed a Planet. In the late 19th century, a massive planet hunting campaign swept through the international astronomy community, with astronomers desperately searching for Vulcan through telescopes, some dedicating their entire lives to the quest. Yet, they never glimpsed Vulcan's true form. It wasn't until the early 20th century that Vulcan's truth was uncovered. What exactly was this celestial body? And how was it ultimately destroyed by Einstein? That's what today's book reveals. Author Thomas Levinson is an MIT professor and director of their graduate science writing program. He's written extensively for PBS and BBC and authored Newton and the Counterfeiter. His science history books, including Einstein in Berlin, have won the Peabody Award, Broadcasting's Pulitzer, and the National Academy's Communication Award. In Chasing Vulcan, Levinson traces from Newton to Einstein, showing how science advances through error correction. I'll explore the book's core through three key questions. First, what exactly was Vulcan? Second, how did astronomers hunt for this planet? Third, how did Einstein completely dismantle Vulcan? Let's begin with the first question. What kind of celestial body was Vulcan? Vulcan's story starts with the 16th century scientific revolution. From the 1500s, modern science's dawn emerged in astronomy. Copernicus proposed heliocentrism, that Earth and planets orbit the sun. Kepler established planetary motion laws showing elliptical orbits. Galileo invented the telescope. This allowed precise celestial observation. But modern astronomy's pinnacle came from a physicist. In 1687, Newton published Principia, founding classical mechanics. Its cornerstone was universal gravitation, mutual attraction between all matter. For example, when you jump, gravity pulls you back to Earth. Similarly, the moon orbits Earth, and Earth orbits the sun, all due to universal gravitation. Moreover, Newton mathematically calculated that this force is proportional to the product of the masses and inversely proportional to the square of the distance. Newtonian mechanics not only helps us understand why things move, but also greatly advances various fields of study. Most importantly, it provided the theoretical foundation for the development of modern astronomy. First, Newtonian mechanics can accurately calculate the orbits of known celestial bodies. Earth and the 5 known planets, Mercury, Venus, Mars, Jupiter, Saturn, along with their moons, could all have their orbits precisely calculated using Newtonian mechanics. Moreover, these calculations matched observational data, for instance predicting solar and lunar eclipses down to the second by computing Earth and Moon orbits. Second, Newtonian mechanics also aided in discovering and verifying new celestial bodies in the solar system. In 1682, Newton's friend, British astronomer Halley, observed a bright comet passing near Earth. Later named Halley's Comet, Halley used Newtonian mechanics and historical data to calculate its orbital period of about 76 years and predicted its return in 1758. In 1758, although Halley had died 16 years prior, people witnessed the comet's return right on schedule. Another example, in 1781, British astronomer William Herschel accidentally observed a moving celestial body and calculated its orbit using Newtonian mechanics. The calculated orbit matched his observational data. This moving body also orbited the Sun and was large. It became the 7th planet, Uranus. By the late 18th century, Newtonian mechanics demonstrated extraordinary prowess in astronomy and was deemed a perfect theory capable of solving any problem. Astronomers at the time believed that astronomy's next step was to use Newtonian mechanics for even more precise orbital calculations. The main challenge they faced was the n-body problem, essentially how multiple celestial bodies influence each other. By then, Newtonian mechanics could easily solve two-body problems by calculating Earth's orbit. Considering only the Sun and Earth, one formula suffices, but Earth's motion is also minutely affected by the moon and other solar system planets. This constitutes the N-body problem. The N-body problem demands complex calculations. A classic example: astronomers observed Jupiter and Saturn unexpectedly accelerating or decelerating. Through meticulous calculations, French astronomer Laplace explained in 1788 that these massive planets strongly influence each other's trajectories when close. By the early 19th century, astronomers could precisely calculate orbits for most known solar system planets. But two planets consistently showed calculation deviations. One was the recently discovered Uranus, the other Mercury, closest to the Sun. Regarding Uranus, astronomers proposed two hypotheses to explain orbital deviations: flaws in Newton's theory itself, or an undiscovered celestial body influencing Uranus. Newtonian mechanics being flawed was unacceptable. It threatened astronomy's foundation. Neptune's discovery in 1846 upheld Newtonian mechanics' authority. Key to Neptune's discovery was French astronomer Urbain Le Verrier. Originally trained in chemistry, a chance opportunity in his 20s led him to astronomy. Compared to veteran astronomers, Le Verrier wasn't the strongest in observation or math, but possessed exceptional intuition. Le Verrier predicted Uranus's anomalies were caused by an undiscovered massive planet beyond its orbit. He even pinpointed its exact location for observation. As an astronomy newcomer, Le Verrier lacked large-scale observation equipment. He sought help everywhere, until German astronomer Gale offered assistance. With Gale's help, using instruments at Berlin's New Royal Observatory, they observed this new planet, Neptune. Neptune's discovery not only reaffirmed Newtonian mechanics but made Le Verrier an overnight sensation in astronomy. And he later became director of the Paris Observatory in 1853. Using this position, Le Verrier focused resources on solving Mercury's orbital anomaly. Mercury's orbital anomaly is also known as Mercury's precession problem. Without other planets' influence, Mercury's solar orbit should be a fixed ellipse. But affected by other planets, Mercury's orbit rotates slightly counterclockwise each revolution. How significant is this rotation? A full circle is 360 degrees. Each degree divides into 60 arc minutes, each arc minute into 60 arc seconds. Observations show Mercury's orbit rotates 565 arc seconds per century, about 0.16 degrees. If you drew an ellipse on paper and rotated it 565 arc seconds, you'd barely notice. But in space, this difference matters significantly. Calculations showed known planets' influence: 527 arc seconds versus observed 565 minus 38 arc seconds gap. Thus, Mercury's calculated orbit differed from observation by 38 arc seconds. Le Verrier believed an undiscovered planet between Mercury and the Sun affected its orbit. Through calculations, he estimated this unknown planet's mass as substantial, possibly Mercury-sized. But such a large planet, unlike distant Neptune, should have been observed long ago. Yet no astronomer had ever seen it. As doubts grew, amateur astronomer Les Carbol gave Le Verrier hope. A French country doctor with a quality telescope in his makeshift observatory. In 1859, he claimed to observe a small dark spot crossing the sun's surface during solar observation, recording its angle and timing. Upon hearing this, Le Verrier traveled to meet Lescarbot and discovered that despite the country doctor having a decent telescope, he lacked formal astronomy training and his watch didn't even have a second hand. All observation times were estimates. But somehow, Lescarbot convinced Le Verrier. Using Lescarbol's data, Le Verrier calculated the planet's orbit, right between Mercury and the Sun. In early 1860, Le Verrier announced the discovery of a new planet, solving Mercury's orbital anomaly. This caused huge excitement in astronomy. Planets are traditionally named after Greek or Roman mythological figures. Following convention, Le Verrier named it Vulcan. Vulcan is the Greek god of fire, and since China's ancient fire deity is Zhurong, it became Zhurong Star in Chinese. All right, that concludes the book's first major question. In astronomy, scientists used Newton's gravity to calculate orbits and predict unknown planets. Mercury's orbital anomalies made astronomers believe in an unknown planet near Mercury, dubbed Vulcan. Yet only amateur astronomer Les Carbault claimed to have seen this elusive Vulcan. If it truly existed, all astronomers should have observed it.
Thus began astronomers' quest to hunt down Vulcan.
Now let's explore the book's second question: how astronomers chased Vulcan. Even if Vulcan existed, observing it would be tough. Planets don't emit light, they only reflect sunlight. If too close to the sun, its light gets drowned out, making it invisible. In 1860, astronomers first tried capturing Vulcan through transits, Les Carbault's method. Ling means to skim across. When a planet passes between Sun and Earth, observers see a small dark dot. Planets closer to the Sun than Earth, like Venus and Mercury, undergo transits. If Vulcan existed, people would repeatedly observe such dark dots crossing the Sun. Astronomers calculated that Vulcan orbits the Sun in under 20 days, observable from the southern hemisphere around late March to early April. However, observatories across Australia, New Zealand, and other nations observed for half a month with zero results. Over the next decade, amateur astronomers from the UK, Turkey, and elsewhere reported seeing Vulcan transiting. Yet the astronomy community dismissed these claims. Why was no genuine Vulcan transit ever confirmed? Some astronomers suspected errors in Vulcan's orbital calculations. In the 1870s, Princeton's Stephen Alexander recalculated Vulcan's orbit, revising its period to about 35 days. Based on this, German astronomer Heinrich Weber reported observing a planetary transit in northeastern China in April 1876, claiming it was Vulcan. News reached Europe, thrilling astronomers including Leverrier. If Weber truly saw Vulcan, transits should recur that October and next March. But both observations failed. In 1877, 66-year-old Leverrier died of liver cancer, filled with regret. Later analysis proved the dark spots seen by Lescarbault, Weber, and others weren't a planet, but sunspots. Sunspots are solar dark patches that move across the surface due to rotation, mimicking planetary transits. With the transit method failing, astronomers turned to total solar eclipses. During totality, the sun's light is blocked, revealing stars normally drowned by its glare. The United States became central to the eclipse hunt for Vulcan.
During America's 1869 eclipse, countless astronomers and amateurs searched for Vulcan, finding nothing. Then in 1878, the year after Leverrier's death, another total eclipse occurred over the U.S.
Total eclipses are only visible from a narrow Earth corridor called the path of totality. This total eclipse path crossed the western U.S. Astronomers chose Rawlins, Wyoming, for observation due to weather considerations. This sparsely populated town sits at 2,150 meters elevation with dry air and excellent atmospheric clarity, perfect for astronomy. Plus, its railroad proximity allowed easy transport of precision instruments. But unexpectedly, sandstorms struck Rawlins on eclipse day, disabling sensitive equipment. Astronomers had to switch to manual telescope observation. Despite harsh conditions, American astronomer James Watson claimed to spot two unknown celestial bodies near the eclipsed sun, especially Body A, which he identified as Vulcan. Quote, accompanying journalists immediately reported it, spreading the news rapidly. Yet after prolonged debate, astronomers concluded bodies A and B were common stars, Beta Cancri and Delta Cancri. Watson directed Ann Arbor Observatory in Michigan, America's first modern observatory, and had discovered over 20 asteroids during prior eclipses. So why did he misidentify them? The author shares an anecdote about Edison rabbit hunting. In 1878, famed inventor Thomas Edison came to eclipse viewing Rawlins, not for Vulcan but to test his new microtasometer invention. He aimed to measure subtle pressure from solar corona's infrared radiation during totality. Though the experiment failed, it didn't dampen Edison's mood. He'd brought a rifle to hunt game. On the platform, a station manager told Edison about local jackrabbits, pointing to a clearing. There's one now. Edison saw a rabbit silhouette, crept closer, and fired multiple shots. But the target didn't react. He finally realized the manager was joking. It was a stuffed toy rabbit, not a real one. Edison didn't hit the rabbit not because he missed, but because the target was wrong from the start. But Edison, eager to hunt game, didn't scrutinize carefully and mistook the fake rabbit for a real one. Similarly, Watson, desperate to discover a new planet, let his desire cloud his judgment during the brief 2-minute eclipse chaos, mistaking known stars for the unknown Vulcan. And that concludes the book's second question, How Astronomers Chased Vulcan. After Leverrier's authoritative announcement, the astronomy community began believing in a large planet Vulcan within Mercury's orbit. However, neither transits nor solar eclipse observations revealed any trace of Vulcan. After the 1878 eclipse observations, many astronomers stopped believing in Vulcan's existence. Some argued that Vulcan wasn't a planet, but a cluster of small asteroids. Each was too small to be seen, extending the Vulcan hunt from 1860 to the early 20th century, a half-century quest. So did Vulcan actually exist? The answer is no, and it was Einstein who shattered the myth of Vulcan. This leads to our third question. In the early 20th century, as physics expanded, scientists realized Newtonian mechanics only applied within limits, not a cure-all. For microscopic particles in high-speed objects, it failed and became inaccurate. Initially, physicists blamed inaccuracies in constants, calculations, or observations, not Newtonian mechanics itself, but that missed the point. Ultimately, scientific theory underwent a revolution. The 20th century physics revolution occurred, centered on relativity and quantum mechanics. It was Einstein and his general relativity that eradicated Vulcan from people's imaginations. As early as 1905, Einstein proposed special relativity. How to understand special relativity? Newtonian mechanics viewed our space-time as absolute, where time flows uniformly and unchangingly. For example, 1 hour in Beijing is always equal to 1 hour in Shanghai, and space is as we intuitively understand it. Three-dimensional space, up, down, front, back, left, right, remains constant. Beijing to Shanghai is always 1,318 kilometers, unchanged at any time.
But in special relativity, the only absolute constant is the speed of light.
At low speeds, Newton's absolute space-time works fine. Time and space seem unchanging. But at high speeds approaching light, Newtonian mechanics fails, causing time dilation and length contraction. Special relativity actually refined and expanded Newtonian mechanics, a major leap. But Einstein wasn't satisfied. Special relativity only applies to uniform motion, even near light speed, hence special. Yet, in reality, we mostly see accelerated motion, like objects speeding up, because objects experience forces, jump from height, and your fall accelerates due to gravity. Earth's gravitational pull prompted Einstein's deeper inquiry. What's the essence of acceleration and gravity? In 1907, though already eminent in physics, Einstein's day job was as a clerk at Bern's Swiss patent office. During breaks, he'd gaze out the window, pondering unsolved problems. One day, seeing a roof repairman nearby, he imagined, what if that man fell? Suddenly, an epiphany. During free fall, before hitting ground, one experiences weightlessness, feeling no body weight. This is identical to floating weightless in space. If falling weightless in a windowless capsule, seeing nothing outside, it would feel exactly like space weightlessness. Thus, the acceleration of falling isn't caused by gravity, so what causes it? Einstein pondered deeper, birthing general relativity's core idea, space-time curvature. In Newtonian mechanics, the core idea is force. It changes an object's motion. If someone pushes you, you can feel it. But in space, planets are so far apart, how does this gravity even work? Like, why does Earth orbit the sun? In Newton's framework, gravity, this invisible hand, seemed utterly mysterious, unexplainable. But Einstein showed we live in warped spacetime. Celestial bodies' mass distorts it, with larger masses creating greater warps nearby. Earth orbits not due to some invisible hand, but because the sun's immense mass curves space-time profoundly. Picture the sun's mass creating a giant dimple around it. Planets orbit by circling this dimple's edge. When we fall toward Earth, we're sliding into its own space-time dimple, just like dropping to a pit's bottom. After refinement, Einstein published General Relativity in 1916. Mercury's orbital anomaly was his first target. General Relativity calculated Mercury's precession as 565 arcseconds per century, matching observations, unlike Newton's 527. So Mercury's orbit wasn't abnormal, Newton's theory was flawed. Why such big calculation differences? Mercury's extreme closeness to the Sun. It's deep in that solar dimple, where relativity's effects magnify. For other planets, both theories yield near-identical results, matching observations. Newtonian mechanics required an imaginary planet to explain Mercury's anomaly. But Einstein's relativity universe had no place for Vulcan. He obliterated it completely. So how was general relativity confirmed? Same as the Vulcan hunt, through total solar eclipse observations. According to general relativity, the sun's space-time curvature causes a slight deflection of light passing nearby, approximately 1.61 arcseconds. In 1919, to confirm general relativity, British astrophysicist Arthur Eddington organized a team to observe a total solar eclipse on Prince Island off West Africa. The results proved that starlight indeed deflects slightly near the sun, matching general relativity's calculations, confirming its correctness. That concludes the third part of the book, How Einstein Completely Destroyed Vulcan. Einstein's special and general relativity changed our understanding of space-time. Specifically, general relativity reveals that gravity's essence is space-time curvature. The mass of celestial bodies warps space-time. According to general relativity's calculations, Mercury's orbit matches observations perfectly. The imagined Vulcan vanished completely. Here we've covered the main content of Chasing Vulcan. For scientists, Vulcan represents a warning. Subjective desires can bias research conclusions. Leverrier, after discovering Neptune, was eager to recreate that glory. Watson, too, was so desperate to find Vulcan. But natural science doesn't advance by human wishes. It's a process of constantly correcting and innovating theories. From this perspective, limitations like Leverrier's were inevitable. Newton's mechanics were their sharp tool for exploring the cosmos. But it also constrained their thinking. As science progressed, Einstein used general relativity to shadow the Vulcan myth, opening new perspectives on the universe. Of course, in scientific history, no detour is wasted. Each setback lifts us higher to see farther. Today, when you gaze at the stars, remember you stand on the shoulders of giants. That concludes our interpretation of Chasing Vulcan. Listening notes are below the audio. See you next time.